One of the most ambitious and difficult solar system exploration initiatives to date was started in August 2018. The Parker Solar Probe set out toward our star aboard a Delta IV heavy launch vehicle. It was long thought to be impossible, then just very tough, but now we humans have succeeded in using a space probe to conduct a closer exploration of the Sun. Our technology has progressed to the point that the Parker Solar Probe might potentially survive the harsh conditions of the Sun for a few years. Watch this video to learn if this technological wonder has indeed completed its orbit around the Sun and what information the probe has provided. The Parker Solar Probe is intended to approach the Sun more closely than any other artificial object has ever done. It is named for Eugene Newman Parker, a pioneer in solar exploration in the United States. Although there have been solar probes in the past, such as the Helios 1 and 2 probes that reached the Sun in the 1970s, all of the earlier probes were only able to do so on orbits that closely matched Mercury's position. Mercury is typically the planet closest to the Sun, coming within 36 million kilometers. In contrast, the Parker Solar Probe will get within 3.7 million kilometers of the Sun. Therefore, we will now receive data from closer to the Sun than ever before, since all of the previous probes studied our star from a safe distance. We have already learned a great deal about the Sun's composition and solar activity thanks to the earlier probes and the observations of space telescopes like Hubble, but scientists still lack sufficient information. We really need to learn more about our star because life on Earth depends so heavily on it. Events like intense solar flares and particle storms, which are launched from the Sun onto Earth's magnetic field, have the power to seriously disrupt life on the planet, especially technological devices. The ferocious solar winds threaten the radio, power supply, and satellites orbiting the planet. It was obvious from the start that this probe would need to be quite different from those that would be sent to Mars, Jupiter, or the outermost regions of the solar system in terms of both design and construction. The Parker Solar Probe must withstand temperatures of about 2300 F since it will fly right into the Sun's corona, which is extremely hot in some regions, and get very close to it. The experts had to come up with several concepts to make this mission technically feasible. In order to safely cover the extremely sensitive measurement devices and maintain a cold head in spite of the heat, the probe first required a housing. A plate-shaped sunshield offers enough protection in addition to the probe's insulated housing. The shield, which is about 9 feet wide and 7 inches thick and is made of unique carbon fibers and white ceramic, shelters the probe so well throughout all flybys that the extremely sensitive measuring instruments are kept within at cool room temperatures at all times. Despite the shield, cameras and sensors can look far enough beyond it to capture both images and measurement data. NASA's solar probe will be able to spend hours in the hostile corona in this manner. The probe is powered by guessed it, solar cells. 2 L-shaped mounted solar cell wings support the 2 primary solar cells. For safety, these wings may be folded in all the way or swung back by up to 75 when approaching the Sun. The probe travels through the hot zone, then retreats from the danger zone at up to 365,000 MP, cools, does various scientific activities during this time, and then returns to the corona a few weeks or months later. Until 2025, this observational game of approach and retreat will be played repeatedly. The NASA specialists have set the mission time at this point, after which there is no assurance the probe will continue to operate. At launch, the Parker Solar Probe already created a stir. "A dream comes true," said astrophysicist Nouri Ali, the mission's scientific director, in a statement about the launch on American television. Ali is from Johns Hopkins University in Washington, D.C. Let's now examine how much of this fantasy will come true as the mission progresses. First and foremost, our Sun is a massive ball of heated plasma without a solid surface that is held together only by gravity. The Sun has a photosphere, chromosphere, and corona. Temperatures in the photosphere, the layer that is most visible to the naked eye, range from roughly 11,200 F at the bottom to 6,700 F at the top. These numbers first don't seem all that remarkable and roughly match the temperatures attained during welding or near lightning. The corona, the outermost layer of the solar atmosphere, is the real enigma of the Sun. Here, some 1,300 miles beyond the photosphere, the sun's temperature can reach 900,000 Fa, which is 80 times higher than the photosphere's measured values. Because the air an inch above the apparent flame is significantly hotter than the flame itself, you may be familiar with this effect from a candle. We have to warn against testing this by poking your finger into a candle flame at this stage, of course. By observing how soon a sparkler ignites when held in the middle of a flame and how quickly it catches fire when held above a candle, you may much more safely confirm this. The size, distances, and magnitudes of the heat effect in the solar corona varied greatly despite this resemblance. This type of temperature differential is often compared by researchers to the way a bonfire heats up with distance. This odd temperature development is most likely caused by hot solar material rising from the outer regions of the sun's plasma layer and getting highly heated by the external magnetic field of the sun. The sun ejects hot solar material into space at a few million miles per hour when these incredibly hot plasma streams break free from the corona and the sun's gravitational field. In 1959, Eugene Parker used the term solar wind to describe this phenomenon. The solar wind causes radio signal interference, power outages, and the amazing auroras on Earth. The intensity of the particle storms varies from time to time. Researchers worry that the sun may one day send a gigantic solar wind our way, which could bring us previously unimaginable issues, even though the extent has so far been bearable for humans. Possible outcomes include a significant disruption of the Earth's magnetic field, which would seriously interfere with navigational aids like those used by aircraft. Changes in the Earth's magnetic field also have an impact on migratory species like whales and birds. Climate change on Earth may also result from a permanent rise in the sun's wind activity. Since learning about the phenomenon, scientists have been keeping an eye on how frequently and how strongly solar winds occur. They were able to see cycles that made the solar winds somewhat predictable as a result. However, the activity suddenly surged in a way that was completely inconsistent with the image painted by the data collected thus far. Soon after, solar storm activity leveled out in a similarly peculiar manner that baffled scientists once more. Astronomers and physicists now want to investigate these whims of the sun and their origin, among other things, directly in the field with the Parker Solar Probe. In April 2021, the Parker Solar Probe made its first full flyby of the sun's corona, which was its first significant accomplishment. In reality, the ultra-thin corona is really dim, and only during solar eclipses can we humans see it clearly from Earth. The photosphere is brighter than the corona the rest of the time. The Parker Solar Probe measured temperatures of around 1,440,000 F during its flyby on April 28, 2021, and transmitted to Earth unique photos of particle streams in its proximity. After taking more observations during the initial flyby, the probe moved away from the close sun a few hours later. The probe traveled at least 5,381 kilometers toward the sun on November 21, 2021. For the first time, the probe was able to capture distinctive solar wind serpentines in the process. Known as switchbacks, these S-shaped plasma streams make one final turn in the direction of the sun before hooking up and heading off as solar wind. The Parker Solar Probe was the first to locate the hook's original location on the sun's visible surface. These convection cells are agitated when heat rises through the sun, forming magnetic energy funnels. Feedback effects have already caused the switchback's S-shaped waves to appear in the funnels. After then, they continue to expand like waves until they reach space. For scientists, the mission is already a huge success. The measurement data and fly-throughs of the Parker Solar Probe thus far mark a significant advancement in solar exploration. This moment is the result of approximately 60 years of human labor. Of course, the namesake of the probe was one individual who was quite happy about this achievement: Eugene N. Parker was enthusiastic about the mission's progress in one of his final interviews. The brilliant scientist passed away in March 2022 at the age of 94, so sadly, he won't survive to witness the upcoming fly-throughs. We hope that this brief visit to the sun was enjoyable and that you gained some new, intriguing insights about our home star. Tell us your thoughts on solar exploration at the end of the video. Do you also believe that understanding the solar winds is crucial, or do you have complete faith in the sun and assume that everything will sort itself out? Please let us know by leaving a comment with your thoughts.